Great. Okay, so welcome everyone to today's UQM seminar. It's a pleasure to welcome Dominic Williamson from Stanford. And Dominic is going to tell us about type 1 non-Abelian fractal spin liquids. So Dominic, take it away.
Yeah, thanks, Mike. And thanks for inviting me to talk at the seminar. It's always a good seminar to attend. So today I wanted to talk about a topic that I thought people in this collaboration would probably appreciate. It's a little bit niche, but it's kind of coming from some exploration in exactly solvable Fracton models that I think is kind of towards maybe one of my last goals in terms of constructing new models, which is basically to try and make some fractal non-Abelian models. And here I'll give you, like, unfortunately not achieving my goal, because I'm only going to talk about, as it says in the title, type 1, as in models that still have string operators in them. But at the end, maybe I'll make some comments about what I'd like to do with type 2 non-Abelian models, and maybe people might have some ideas about that. That would be great. But yes, let me tell you what I'm going to actually talk about, which won't be type 2, it'll only be type 1 fractal models. So if you kind of had one of the few people who had read this paper I wrote with Meng last year, today's talk is sort of in some ways a sort of a generalization of this, and that's not actually a huge generalization. And in that work, we basically made some construction where you could input different topological layers that are drawn on the XY plane here that have a certain abelian boson. And then you take some string operators of this abelian boson in planes, and you treat this as a symmetry and then gauge these planes along a cubic lattice, and this produces for you some Fracton model. And the main feature of this Fracton model that was interesting is that by plugging in different layers here, you could get a very large array of different fractons in the Fracton model. And in particular, they could be sort of non-Abelian and have non-integer quantum dimensions squared and have interesting braiding properties. So the new construction is following on from this. And it's just basically one extra idea that I realized that you don't need these symmetries to be in planes, basically. You have like this basic symmetry, which is like a string operator in a single topological layer. So the setup for the topological layers is the same. You have these layers that contain some abelian boson. You have the string operators for that. And you can arrange these string operators so that they're in lines along one direction of the layer, but along the other axis that the layers are stacked in, they have this sort of fractal pattern instead of just coming in a plane. And this is a perfectly good symmetry of these layers, and you can gauge this. And it ends up coupling your layers to some fractal gauge fields, if you like. I'll just call that for lack of better words. And these gauge fields, these sort of, let's say if this is a Z2 symmetry, these Z2 gauge fields are related to this fractal spin liquid model by Yoshida. And I'll explain this all in much more detail when I get to it, but that's sort of the overview. So sort of if you knew the previous the previous work and you knew this paper by Benny, then if you kind of combine these, this is the new idea. Cool, great. So the background for what I'm going to talk about is I'll be thinking about Hamiltonian systems that have an energy gap, so a gap in the spectrum when you sort of take the continuum limit. And I want to impose this condition of topological order. I think there's some kind of confusion, or people use the word topological order in different ways, sort of coming from quantum code community, where it's used sort of synonymously with this sort of code condition that if you take, you have this Hamiltonian and you have any local operator and you project it into the degenerate ground space. Let's assume for purposes of discussion, we're on like a torus or something, so it's a ground space degeneracy. And when you project these local operators into the ground space, you just get a C number that can depend on the operator. Okay. So this doesn't say anything about sort of deformability or anything like that. So maybe this is why it's actually not so great to call this topological order, but I'm going to call this topological order for the purposes of this talk. Okay. And then the thing I'll be interested in is sort of models and phenomena of these models up to this equivalence relation, that sort of smooth deformations preserving the gap. I'm not going to talk that much about classification, so the specifics aren't that important, but yeah, we don't care about so much about any particular Hamiltonian, just this equivalence class of Hamiltonians and some universal properties of those. Okay, great. And then what do we know so far? So in 1D and 2D, the story is like largely resolved for these gapped models. Okay, up to, you know, maybe not mathematically rigorously in 2D, but in terms of like physics, I think we kind of know what's going on with these models. And then in 3D, things get more complicated. So in recent years, there's been a lot of progress on this kind of axis. So if I kind of have this toy sort of phase diagram of all 3D gapped Hamiltonian systems with topological order, I can have, of course, a trivial phase. And then on this sort of axis, I'm indicating there's like sort of TQFT-like things. We have this framework of TQFT. It's a nice mathematical subject, and you can kind of put conditions on lattice models so that they act like TQFTs. And you can make a lot of progress on classifying these things. And maybe at this point, it's actually like kind of pretty, it's a beyond sort of physics rigor, this classification. I think some mathematicians have worked on it too, but I should say the idea is like initially due to Lan, Kong, and Wen. And you can kind of classify all these TQFTs. So we understand them pretty well. On this other axis, we kind of have the stack of 2D TQFTs. So I was showing this sort of stack earlier before coupling. This thing is a perfectly well-defined 3D Hamiltonian, but it's kind of strange because the super selection sectors in particular depend on the number of layers you include. But okay, it's not that much more interesting than just a 2D TQFT. So we understand this axis pretty well too. And then we have sort of everything else that is beyond this, which we are basically just going to call all these things Fractal topological orders. In some sense, this stack of 2D TQFTs is kind of like a trivial Fractal topological order. So let's just call these sort of the non-trivial Fractal topological orders. And often it's said that these sort of things are beyond TQFT, like beyond a 3D TQFT or a stack of 2D ones. But maybe I'll mention a bit some work that's from last year that's sort of saying this is not so true, and maybe these things are actually captured by TQFT plus defects. But nevertheless, if you just look at these models, their behavior depends on exact length scale of the lattice and other things like this. That's quite strange and does not look like a TQFT behavior. And these are the kind of models I want to talk about today. Okay, so I should give you an example to establish some terminology that I'll continue to use. Sorry, let me just move the Zoom window. So the simplest example of this, I think, kind of model, a non-trivial fractal model, is the X-cube model, which hopefully everyone's seen before, because I'm not going to go into detail of explaining it. But I'm just going to show you the super selection sectors of this model. So there's sort of two sectors. It lives on a cubic lattice. I've put the excitations on the vertices of the cubic lattice. And in one sector, you have these sort of fractons, which are drawn in white here. They have like Z2 stacking rule, and they can be created at corners of these squares, basically. And so then you can stack these squares on the faces of the cubic lattice with the Z2 stacking rule and make all sorts of charge patterns. The most basic property is that a single one of these fractal excitations can't hop by one site without creating more. So if you kind of have one here and you hop it to here, sorry, can people see my cursor? I just realized okay, hopefully people can see my cursor. Otherwise,
we can't see.
No.
Oh no, okay. Maybe I can do laser. Here we go. Great. Oops.
Still can't see it.
Huh. Oh, okay, great. Can you see this arrow?
Yeah, I can see that thing.
Okay, good. So yeah, if you hop from here to here, you create these two extra excitations. So there's no way to hop without creating more excitations. So this is basically what defines a fracton excitation. You can also make more complicated patterns of these excitations. And in particular, if you pair two of them up like here, you can move, in a plane orthogonal to this sort of line connecting them. So we call this a planon. Okay. And then in the other sector, we have a sort of Z2 times Z2 fusion, which is shown here in these different colors. And each of these excitations can move along some direction. So we call it a line-on because it can move in a line. It can only move in one direction without creating further excitations. But the three different colors have some overall fusion rule that they can all fuse to trivial, which allows, I think shown here, that you can turn corners up to creating some extra excitation. And so if you pair two of these guys up, these extra excitations you make at the corners, you can annihilate them, and it allows a pair to be a planon. Okay, so this is sort of the simplest example, and it has a lot of the different parts I'm going to talk about later. It doesn't have these kind of excitations that are moved by fractal shape operators, but I'll come to an example with that later. Okay, great. Oh, yes, good. So one point of view on these fracton phases that I'm going to be using a bit in this talk is as some kind of generalized lattice gauge theories. And this was some work from kind of early on in this interest about fractons, where it was realized you could take these sort of simple Ising models that are defined on sort of cubic lattices, and they have Z fields that instead of being two-body Z fields are sort of more complicated, such as this plaquette Z field here. This gives rise to symmetries that instead of being like a global symmetry, or even some deformable higher form symmetry, are these like rigid symmetries, which can live on, for example, planes, which is in this example. And then you can do this duality of sort of gauging the symmetry, which I don't want to go into too much detail for this example, but you switch to different variables, and then it will generically turn like a trivial phase into a topological phase, and it'll turn this simple like plaquette Ising model into this X-cube model I showed you previously. Okay. You can also have more interesting, from my point of view, Ising models that have constraints that give rise to these sort of fractal or discrete fractal symmetries. So in this case, the symmetry is more like some kind of 3D fractal pattern. This is just a picture for illustration. And again, you can do this gauging duality. And this example actually gives you this famous cubic code model of Zhongwen Ha, which is this type 2, which I should say what that means. So this type 1 means basically you have some sort of string operator, and type 2 means that in the model there are no string operators whatsoever. So that these topological sectors, they can't move, but you can't sort of pair them up in any way without them becoming just totally trivial that lets them move. So this is kind of the most interesting type of model from an error correction point of view, I think. And I think there's still sort of some interesting questions about making new models of this type. These have been sort of less common, let's say, than the other construction so far. Great. So now, before getting to the new construction, I want to give a bit of a review, but I might try and make this kind of a lightning round of previous non-Abelian Fractal models. And I know I definitely haven't covered everything, so I'm sorry to people I miss. But I've sort of erred on the side of covering models I know, so I'm probably a bit biased towards myself too. Sorry about that. So I think the first construction I know of is this model by Ha and Fu, who sort of made the point that if we have these restrained mobility of point-like excitations in 3D, they no longer have to be bosons or fermions. So they can kind of be more interesting, and they could be non-Abelian, for example. So in their construction, they take these P plus IP layers that have these Majorana zero modes at the vortices, and they kind of gauge these in a funny way. So instead of like gauging them in the usual way, where you would gauge each layer separately and you'd be left with a layer system at the end, they gauge them by coupling them to this like gauge fields of this Majorana checkerboard model, or they treat this model as like the gauge fields in some way. I don't want to get into the details of this construction, but you can do this consistently. And then you get this funny model that has very similar sectors to this Majorana checkerboard model, which again is pretty similar to the X-cube model for our purposes. But you've kind of tied this vortex to the fracton particle. So this becomes non-Abelian with quantum dimension √2. Okay, let's go to the next example. So I think this example is very interesting, but it was sort of a one-off. It didn't have reconfigurable pieces so much. But then there came some follow-up papers, I think, which were looking at some class of examples where you could really put in some data and you could just switch it out within the same model to get like a whole family of models. So the simplest type I know of this is that gives you a non-Abelian fracton is these models due to Song et al. That basically took something like this checkerboard model, which for our purposes is like two copies of the X-cube model. So this is like the spin checkerboard model, not the Majorana one I mentioned previously. That only has the effect of basically making it two copies of X-cube instead of one. And they devised some way of basically introducing like SPT like co-cycle twists onto layers. So they can do it in all three directions, but here I'm just showing one direction. And if you pick sort of the right gauge group and then co-cycle twist here, you can get non-Abelian fractons. Sort of analogously to how you get non-Abelian particles in like a twisted gauge theory in 2D. So basically the fluxes of this SPT layers become fractons. So if you had like some projective rep on this flux that has dimension 2, say, you'll get some non-Abelian fracton here with quantum dimension 2. Okay. So that example was nice because it let you kind of just input a bunch of data into the same models and get a whole family of constructions. But let's move on to another nice construction that was sort of allowing even more general ingredients. So this is the CageNet models of Prem and Huang Song, I think, Hermele, which follow on an earlier construction due to Saga and also Xie and Mike and Ethan and Han, I think. Yes. Okay, so this construction is quite similar to the previous one. You plug in a bunch of layers, but this time these layers are 2D topological orders, not SPTs. And you need these topological orders to contain a boson particle, which I'm drawing in red here. Let me get my little pointer. Whoops. Okay, yes, so I've called this boson B. And then you imagine these like p-string composite excitations where you draw some string through the layers and call this, everywhere it pierces the layers, you attach this B boson and you call this a p-string excitation. So here I've drawn an open one, but you can also have these in loops. And then you induce some coupling. So you sort of stack layers in all three directions if you want an interesting model, and you introduce some coupling that basically condenses these p strings. So it doesn't condense single B, but only in these composite excitation strings, it condenses these. And this has the effect of coupling these different layers together into what they call the CageNet model. They call it this because it has this funny wave function that basically takes string types, certain string types, and forms them into cages. And you have these cages fluctuating over the lattice. And at a sort of an immersion theory level, it takes any anion, which could be non-Abelian, for example, even though this boson has to be abelian. Any anion in the layer that braids non-trivially with this boson is going to get promoted, in this case, into a linon. So this kind of, although in this model, the fractons end up being abelian, you can have like a lot of freedom over picking your linons. And I should say that the excitations in this model are pretty similar again to the X-cube phenomenology, except you can sort of make the linons non-Abelian. And this is cool because you can kind of plug in, even more sort of general things in these layers as long as you have these abelian bosons. Okay, so I switched from talking about gauging to talking about this condensation, but actually it's not so different. I just want to say one word about that, which isn't super important, but you can view this condensation as basically gauging a certain kind of symmetry. So you had these B bosons in the layers. And so if I take the string operators of these things and I consider some sort of one-form symmetry in 3D, so on surfaces like spheres, everywhere it passes through some layer, I attach some line of this string operator for the B boson. This will give me some symmetry of these layers. And then if I gauge this symmetry, just this sort of 3D surface-like symmetry, where everywhere it passes through a layer, I attach this string operator. This will be the same thing as condensing domain walls of the same symmetry. And the domain walls of this symmetry, basically where these string operators end, is exactly a P string. So basically gauging this one-form symmetry of these string operators is the same thing as condensing these P strings. And it will give you a sort of a different, slightly different lattice model, but basically it's the same emergent phase. So by doing this, you get these string membrane net models. Okay, so in this case, it was a bit different to the previous ones. We were kind of gauging a more, in some ways, usual symmetry, the one-form symmetry, but then because we were gauging it on layers, we could still make a Fracton model. Okay, so I think that sort of inspired us to think, how could we do something that has the feature of like the CageNet models, but also this more property that the non-Abelian particle could become a Fracton rather than a linon. And we looked at a different subgroup of this big symmetry group of these layers, where instead of having the symmetries live on some two manifolds, we only consider a subset of those two manifolds, the ones that are just planes. So we consider some set of planes on these layers. So we stack the layers just in one direction, like along the z direction here. And then we consider having some planes in xz and yz. And we'll make a grid of them. So here I've just drawn one, but we want to make a grid of these to get a non-trivial model. So put them at different locations. And then we will gauge these like line operators for the same B boson on these planes. Okay, and the effect this has is basically it will kill the sort of hopping operators that don't commute with these string operators on these planes, which means that if you have like a single anion, which can be non-Abelian, even though these string operators are Abelian, that braids non-trivially, when you gauge this thing, it becomes a Fracton. So you can get like a non-Abelian Fractons this way, and you really can have a lot of control over what you put in as long as it contains this abelian boson. And you can get, for example, non-integer quantum dimension squared and quite interesting braiding from these things. And once again, this is just sort of, in some ways, it's a different generalization of the X-cube model. So generalizing the X-cube model in a different way than the cage nets. But in this way, instead of getting non-Abelian linons, you kind of get non-Abelian fractons.
Dominic, could I ask,
Mm-hmm.
So to clarify, when you think about subsystem symmetry in this very general way, for the Ising-Plaquette model, I can see explicitly what it meant, right? You flip a certain number of spins on the part of the system. How do you think about this abstractly when you're looking at the model on the left? What exactly does the subsystem symmetry refers to?
Right, so the subsystem symmetry, we need to introduce some kind of lattice. So it's probably easiest, or it's most clear with a microscopic lattice, but we can actually give constructions of these models that don't refer to this microscopic lattice using this sort of topological defect network framework that I'll mention in a second. But let's say we have like a lattice scale, then we have these layers that are, say, given by string nets, and we can write down these like string operators in the string nets. And so we'll put these string nets onto we'll coarse grain them so they're on like a square lattice. And then you have this string operator for this B boson in the string net. And the way the symmetry will act on this lattice model is by like the product of this string operator on all these layers together in a plane.
I see. So it's not just one topological order in individual planes. They're sort of coupled to each other by a string. Is that?
Yeah. So before doing this sort of gauging construction, they're just decoupled layers. And then you have the symmetry that's kind of acting on all of them together. So you don't gauge each like individual line separately, only the plane of them. And by doing this, by only gauging these symmetries that act over all the planes at the same time, it does couple them together. So this thing on the right here has like a lattice model description.
And before you gauge, sorry, maybe I didn't catch it at first. Before you gauge, if you talk again about the system on the left, is it enough to take a toric code and a square lattice? That doesn't have subsystem symmetry, does it?
I guess in the lattice model, from my point of view, I would say there are some operators that look like subsystem symmetries. It kind of, in some sense, is breaking these symmetries, but it has like this one form, the actions of these like one form operators. So you have one for E and one for M, and then there's some, I guess, braiding between them. And so if we just pick, say, the M boson, we'll have these line operators for that. And in this setting, if it was a torus, I guess those would act non-trivially within the ground space. And it's that we're gauging, the product of those over all the layers. So if this B boson was M in the toric code layer, then this A would be like the E particle or the psi particle. In that case, you wouldn't get a non-Abelian fracton, but you basically actually end up just getting X cube. So when I say it's a generalization of X cube, if you plug in toric code layers and you gauge, like, say, this M string operators in these planes, then you'll get exactly X cube, well, up to local unitary. Okay.
Thanks.
Great. Yeah, sorry, I've given a different talk kind of explaining this whole model, and it's kind of hard to explain all the features of it in a whole talk, so it's probably not super clear. But yeah, let me just give another flavor for it. So again, using this correspondence between this kind of gauging and condensing the domain walls, this planar gauging is actually very similar to P string condensation, except the difference is, like, why does it let you get non-Abelian fractons instead of linons? Because we're kind of confining these P strings now to live in these planes. So they don't fluctuate over the whole sort of 3D space. They only fluctuate over these 2D planes. And you have like sort of an independent P string condensate for each of the planes, basically. So that's just another point of view on what this gauging is doing. And you can use this in sort of two different ways. So if you want to get a fractal model, you can start with layers stacked in one direction shown by these blue layers, and then consider these P string planes in two other directions. Like, say this is along the Z direction, then you have XZ and YZ planes. And if you condense these P strings in like a grid of these XZ and YZ planes, you end up getting this generalization of the X cube model. But you can also do a different thing where you stack the topological layers along two directions. So say in these XY and XZ planes like this, and then you condense the P strings in one set of planes, say along this like X direction here. And this results in like yet another generalization of the X cube model, if you like. But this one's kind of cool because the planes don't intersect. You don't have the constraint that the things you're condensing on the planes have to be bosons. So you can actually do this P-loop condensation of like chiral anions that are abelian. which lets you get some interesting models. Okay, so that's everything I think I want to say about. Oh no, sorry, I want to say one more thing about this planar p-loop condensation. So this has also been used in some other model where you have like a toric code that has some non-trivial symmetry enrichment by some planar subsystem symmetries, which have like effectively, a projective rep on the string excitation in the 3D toric code. And again, you can kind of do this gauging of the subsystem symmetries. In this case, you get a non-Abelian fracton with integer quantum dimension, but you have this funny model that also has these kind of, which at some point we called panoptic, which has like these point particles that have 3D mobility as well. And this is kind of because you have this funny gauge structure where you have two kind of planar gauge groups coming from the planar symmetries, and then you have this global gauge group, which gives you the 3D particles. But the reason that you kind of get something non-Abelian is because they're tied together by something like a type 3 group co-cycle. Okay, so that can happen. And then I think the final little example I want to mention. Yes.
What do you mean by the global gauge group?
Yeah, so this is very loose wording, but you can view all this as sort of like an SPT where it has like a Z2 times Z2 subsystem symmetry on planes, and also like a Z2 global symmetry on the SPT side. And you can just take this whole group and then gauge the whole thing to jump from the SPT directly to this non-Abelian model here. So I guess that, but by this thing, I mean whatever this gauge structure is you get on this model by gauging something that was a Z2 planar times Z2 planar times Z2 global symmetry in the first place. Hopefully that makes enough sense. It's definitely not very precise. Okay. I think, sorry, this is the final example I wanted to recap because it has some, it might be in some ways the closest to what we're trying to achieve in this talk. So this example was trying to sort of get more interesting, say, type 2 non-Abelian fractons, although it also failed to achieve this. And the idea was to start with bilayers or more multiple copies. You get some global symmetry of this. So and on these layers you can put whatever fracton models you like. Say for example X cube or cubic code, which could have type 2 fractons in it. And then you have this symmetry action, which is kind of obvious, which is swapping the layers. So in the simplest case, it's just Z2 swap. And you gauge this global symmetry. Okay. And this promotes the fracton that gets permuted by this symmetry into a non-Abelian fracton with integer quantum dimension. Unfortunately, it also introduces this sort of panoptic phenomena where you also have these point-like excitations that are mobile in 3D, and you have some weird non-Abelian loop excitations. So it ends up being that this model is not type 2 because it has string operators, even if what you started with was type 2. But this is some interesting example where you do get sort of fractal operators as well as a whole bunch of other stuff. And in a very loose, again, sense, it has like this interesting gauge structure where there's kind of this Z2 fractal gauge structure, say, coming from your one copy of your model and then another copy of that from the other copy. And then you have this kind of global symmetry that's swapping them. And you're kind of gauging all of this. And so you get this funny gauge group. Okay. So I gave you a lot of examples. Maybe they weren't all that well explained, but recently we have some kind of nice formalism where we think we can fit all of the examples, at least with finite sort of excitation order on diffusion into. And the idea is that you can fit all this into TQFT. And this is kind of nice in that it lets you abstract away the like lattice scale a bit. You can take this lattice scale going to 0 of the microscopic lattice and just keep this defect network lattice scale. And on this defect network lattice scale, you plug in ingredients coming from TQFT with defects. So on what we call the 3 strata, like the 3 cells of, say, a cubic lattice, you plug in these 3D pieces of TQFT. And on the 2 strata where they meet, there are kind of these defects, which can be non-topological defects, or domain walls, which can be non-invertible. Usually you want to pick them non-invertible to get something non-trivial. And then where they meet, there's some sort of like one-dimensional defect or interface of all of these things around it, which also has some topological data describing it. And then finally, there's some point charge you pick as well. This is kind of nice because it lets you sort of construct models without having to refer to the microscopic lattice and in terms of this TQFT ingredients. And then you can sort of understand the model you get from how the excitations in these TQFTs can move given the defects. Great. And in this construction, we were able to find this a D4, an example based on D4 gauge theory that ends up having a non-Abelian fracton. Although it's sort of like the previous example I showed you in that it has also some mobile abelian particles. And the way you get it roughly, I think I'm not going to explain it in too much detail, is that in the 3 strata, you put these default gauge theories. It has this non-Abelian particle, and then it has this abelian sort of flux loop. And on the 2 strata, you condense this flux loop basically. And this braids with the non-Abelian particle. So because you've condensed it, it's no longer allowed to jump between these 3 strata, and it gets sort of stuck without creating further excitations at least. And I should say as well, within this topological defect network, we found this one sort of new model, but actually I think it's it can realize this as one of these sort of generalized string membrane net models. And this topological defect network is capable of describing like all of these string membrane net models and the sort of gauge layer models I showed you before. And the model I'm going to show you in a minute is also, can be phrased in a topological defect network. And probably there's some other stuff too that I'm forgetting that you can also describe with this. So, hopefully everything that has finite order of fusion can be described in this way, I think is currently the conjecture. Great. Yeah, so I have to tell you one more thing before I tell you the new model, which is a little bit more details about Benny Yoshida's fractal spin liquid models. So I'm not going to put the non-Abelian in yet, but I'm just going to describe to you kind of the sort of fractal line symmetry and also the kind of gauged version of this model that he had in his 2013 paper. Okay. Good. So Benny has this construction, which is kind of cool because it gives you a whole family of potentially fractonic models that have some interesting behaviors. And what you plug into this is actually 2 cellular automata rules. So there's some linear cellular automata, which tells you how you kind of evolve from one layer to the next. So in this case, I picked the Sierpinski rule, which is just 1 plus x, which means that when I hop down by 1 layer, I put in a pair of z's spread out like this. For the subclass of the models I want to talk about here, in the other direction, I'm just going to pick the trivial rule, which means that I just have these pairwise z's. So these constraints define some Ising model basically, and some sort of weird symmetry on this Ising model that's kind of fractal in one plane here, like the YZ plane, but along the x direction, it's just kind of like linear. So basically what I get is like these symmetries that act on all of 3D space of this lattice model, but they are sort of inhomogeneous. So along the x direction, they're boring. They're just like lines of just spin flips in this case, because it's just an Ising model. And then in the other plane, there are these fractal patterns. Okay.
Dominic, sorry.
Yes, please.
This went a bit too fast for me, and I apologize if this is trivial, but I'm not familiar with Sierpinski automata. So what does this 1 plus x refer to again? Could you again explain geometrically?
Yeah, sorry. I actually did explain this, but I think I switched the order of slides a bit. So it's out of order, sorry, but maybe let me come back to saying exactly what this notation means. But here, let's forget this like whatever notation and just say you can pick any shape you like in this sort of YZ plane that is determined by some update rule given by a cellular automata, basically. So there's some rule that tells you if I have like a symmetry on the previous row, when I go to the next row, where do I put the symmetries? And it's sort of local. So it's not going to put one like way over here. If I started with, sorry, you can't see my cursor. If I start with some symmetry line here, then I want to see how the symmetry has to extend to the next row. It's not going to extend all the way over here. This rule has to be kind of local, but with this Sierpinski rule, basically it's going to extend in such a way that if I look in this plane here, it's going to look like Sierpinski gasket. So if I continue this and keep evolving it, it's some discretized version of like the Sierpinski triangle. So that for now, that's what I mean. And then, sorry, I'll explain this notation in a minute. Great. So I have this symmetry, and I'm going to call these the type 1 subclass of the fractal spin liquid models, where I have this line in one direction and the fractal in the other direction. And there's quite a lot of configurability in this. You can pick different cellular automata as you like to get different shapes besides Sierpinski. But I think for everything I'm going to show you here, I'm just going to use the Sierpinski as an example and also stick to Z2. You can also generalize this to any Abelian group you like. Okay, so yeah, you can do the gauging duality on this model, and it turns into this other model, which now has variables living on, so 1 spin per X edge and 1 spin per this triangular YZ face. It's not super important exactly the way this Hamiltonian looks. let me tell you what it means for the excitations. So the excitations end up being basically, they can move the way that the symmetry charge moved before. So this is for the gauge, what I'm calling these fractal line-on gauge charges. And then for the fluxes, they're actually sort of dual. So they have exactly the same mobility, but just sort of an inverted lattice. So I'm just going to show you the charges here for now. And the fluxes are just the same, but you kind of invert the space. Okay, so the way these move is if you have like a Z operator on one of the links, you can see it'll excite two of these X kind of terms, which are the gauge charges. And this allows this charge to hop along the X direction. And if you have one of these Z's on one of these triangle plaquettes, then it creates a, in this case, trio of these charges. And you can use this sort of trio to move these charges and spread them out in this XZ plane. And due to the input of this sort of Sierpinski rule, the way these operators move is that they can kind of be, these excitations move is that they can be created at the corners of the Sierpinski triangle. And by corners, I mean sort of the unpaired vertices of these triangles under Z2 stacking. Okay, and I'll show you an example of kind of moving these around in the defect network language in a minute. So I think the final thing I want to show you before telling you how to insert the non-Abelian part is the defect network description of this model. So for this defect network description, which lets us kind of throw away the microscopic lattice, we put in 3D toric code, or Z2 gauge theory, if you like, on the 3 strata. The 3 strata I'm drawing as these kind of bars of triangular pyramid, I feel like. You could draw these so they look more like the 3 strata in the previous example, in the previous picture of the defect network I showed you, with kind of trivial domain walls along the X direction, but okay, I didn't do that because it's kind of superfluous. Okay, within these blocks of this toric code, you have like M flux loops and E particles. So those are the excitations we're going to talk about. The 2 strata, so the faces of these, the boundary condition I pick on all of them is just flux condensing. So the E charge doesn't condense there. It just goes to the boundary and stays as an E charge, not interesting. But the flux loop can become a flux arc. So it can sort of, you can push part of the flux loop into the boundary now, which gives you this kind of flux arc excitation in the vicinity of these boundaries. And now the final thing I have to tell you to determine the defect network, because in this case, there's sort of, the 0 strata are kind of trivial because everything's just running along in the X direction in a kind of trivial way. The final thing I have to tell you is the 1 strata. So let me just get rid of the bigger picture for a second and focus on a single 1 strata. And near this 1 strata, the relevant excitations are this E particle and each of the different blocks meeting there, and this M flux arc that sort of straddles either side of the domain wall that's touching this 1 strata. Okay. Now, to describe this in a sort of easier way, you can kind of stretch out. There's this trick where you just sort of stretch out these blocks coming in of 3D toric code so that they kind of become thin and narrow, actually like 2D. So I'm drawing like the perspective here, but everything runs back into the board. So each of these blocks is 3D, and this line here is 2D. Sorry, I should point to the line. Like these lines here, 2D. Okay, and now we just need to describe how the excitations kind of condense in these 2D layers around this 1 strata. So what is in this 2D layer when I kind of stretch out this 3D toric code with these flux condensing boundaries? I can move the M flux arc into this 2D layer, and I can also move the E particle into there. And it turns out that in each of these 2D layers, so now I've just sort of focused in on the 1 strata and just forget the larger sort of stuff going on around it. I actually just have layers of 2D toric code coming in. So that's what you get when you kind of squeeze or compactify this 3D toric code with these flux condensing boundaries. Great. And yes, to describe this 1 strata, I'm just going to treat it as a gap boundary. So I fold everything, just some do nothing move to rearrange it. And then I can view this as 3 layers of Z2 toric code with some gap boundary to vacuum. And so we know this gap boundary is described by Lagrangian algebra. In this case, the correct object to pick if you want to recover the right excitation behavior of this Sierpinski fractal spin liquid is the triple of E's condensed there and pairs of M's. Great. So this is just some choice I make, and let me show you how it works. So if we go back and unfold everything and see what this means for the 3D model, now, because I had pairs of M's condensing, these things kind of blow back up into these M arcs. So I have these arcs of M that can hop through this one strata. And then I have this triple of E's, so I can create this little cluster of E excitations around the one strata. Great. To see that this gives me the right excitation property, I want to show you first that the M arc basically plays the role of this fractal gauge charge. So you can take from nothing, you can make a local operator that makes some flux loop. You can push this into these corners by condensing it into the boundary. And then you can use these one strata moves basically to hop this arc through the one strata. You can then use the deformability of this flux loop within one of the 3D torque code blocks to bring these arcs and sort of condense part of it into the boundary and make two arcs near the one strata again. And then two of these cancel out in the middle because each of them hops onto the same location and it's got a Z2 fusion rule, so you end up with nothing there. The other two don't cancel out. And this kind of gives you this fractal sort of cascading pattern of these excitations. So if you continue doing this, they're kind of moving on the unpaired corners of this Sierpinski triangle. And you can sort of continue moving them to isolate these excitations as far apart as you like from each other. Great. Now let me show you the other sector. So in this case, E plays the role of this fractal gauge flux. And if you use this sort of hopping rule of one E to a pair of E's, because all three of them condense at the one strata, you can then use the mobility of E within the block of torque code to push it to the next level of one strata and hop these through again. And then you can pair up this pair that ends up being on the same block of torque code and just fuse them to vacuum. And you see that you have this kind of same, well, the same sort of behavior or hopping of the E charges, except now it's going in the other direction. And these excitations do have some braiding, which is just inherited from the 3 torque code. So the E and the M have like a -1 braiding phase, which is the same as in the fractal spin liquid, which I don't think I mentioned actually. Okay, great. So now I want to tell you quickly how you add the non-Abelian element to this. So the idea is to take these layers. So we have some 2D topological layers that contain some Abelian boson. Let's say a Z2 boson for the simplest example. And now I want to describe this weird symmetry I'm considering, which is like the same, well, isomorphic to the symmetry of the fractal spin liquid. And I'm using this polynomial notation. So you get to input into this, besides the layer with the boson, also some cellular automata rule. And in this case, I picked the Sierpinski rule. And as I sort of go up a layer by multiplying with Z, I multiply this also with this cellular automata rule, which in this case is 1 plus X, to find where these string operators should be. So this is what's going to define my symmetry. So if I expand this out in this example, I get this. And basically this notation, to answer the early question, is just basically the powers are telling you the coordinate of where these string operators are landing. So let me convert this to coordinates, just basically rewriting the powers into the coordinates. And in this case, I know that I want these all to run along the full Y axis. So I'm just going to put a dash in the Y coordinate. So that's how this cellular automata rule works. You just have some update rule, which is multiplication with this polynomials over Z2 in this case. And this is what's going to define the symmetry. So this cellular automata rule and these string operators. Okay. So now this is the symmetry I want to gauge. And I can gauge it by using the same kind of gauging map as for the fractal spin liquid, or the same sort of defect network, which I'll show you in a second. And if I want to get fractons, I need to actually do this in 2 directions. And this is consistent so long as the string operators in both directions are bosons and they braid trivially with each other. I can kind of gauge both directions at once. Great. So let me come to this. What am I going to be condensing by gauging these things? So if I kind of cut open this symmetry somewhere, what I get at the domain wall is this like fractal of these B bosons. So instead of being like a string of these B bosons, it's a fractal. So I'll call it a P fractal. And then gauging these symmetries condenses these P fractals, if you like. So it's a bit less obvious just to see from that picture what's actually going to happen. So yes, I have this construction. I'm taking these funny symmetries, gauging them to get what I'm going to call the type 1 non-Abelian fractal spin liquid model. If I had initially input non-Abelian layers. Okay, great. And so how do the excitations behave in this thing? If I have some excitation, which I'm going to give a subscript minus to mean that it braids non-trivially with the B boson, then in the gauge model, it becomes a fracton. And the reason for this is if I try to move it in either direction, it makes these fractal gauge charges. So just the same gauge charges in the fractal spin liquid model I showed you a minute ago. It makes these fractal gauge charges everywhere that one of these string operators acted in my grid. And these are sort of line-ons in the direction. Sorry, let me get my spotlight. These are line-ons along this axis that's kind of orthogonal to the direction of this string, but they can't move freely within the direction of this string operator. So along this string operator direction, they kind of have this fractal mobility, which means that, if I kind of make a big string, like all the particles along that string are not going to just be cancelable. So basically moving this A- particle in either direction is going to create this big string of excitations, which makes it a fracton because it can't move in either direction. And it also can't move, in the Z direction because it's kind of confined to a layer without creating further excitations. Okay, great. The A+ anyons, which is the other part of the anyon theory in the layer that basically braid trivially with the B boson, just remain planons because they don't talk to these gauge fields at all, basically. And then let me give you a summary of what happens with the fractal gauge excitation as well. So I said that we have these A+ planons, which in this case, if B is a boson, includes B. We have these A- fractons, A- particles, which become fractons. And these in particular can be non-Abelian with non-integer quantum dimension squared, can be quite interesting and have interesting braidings. All they need to satisfy is that in their 2D theory, they braid with some boson. The fractal gauge charges in this case were equivalent to fractal gauge charges from the fractal spin liquid layers, which I coupled to. And so these end up being X or Y line-ons, depending on the direction I'm moving. But if it's an X line-on, for example, in the YZ plane, it's kind of moves in this fractal way. And these are kind of coupled non-trivially to the layers, because if I take a pair of these fractons, equivalent to say hopping one fracton, this is going to be the same as or equivalent to the gauge charge in this previous picture. And then to be consistent with this rule, the fractal gauge flux has to talk to the layer as well. And actually what happens is that this kind of trivial cluster of the fractal gauge flux excitations ends up being equivalent to a B. So this is to make the braiding of these fractal gauge charge and flux consistent with the fact that they are related to the A- anyons and the B anyon in the layer. Okay, so this is kind of full summary of that. I think I've gone a bit over time, so that could be a good place to stop. But if anyone wants to ask me, I can show you the topological defect network for these things and some examples. Thanks.
Thanks, Dominic. So does anyone have any questions?
Hi, I have a question. I'm confused about the concept of non-Abelian fracton. So if I understand correctly, you're starting with a thing which is a non-Abelian anyon in 2 dimensions, and then somehow getting it stuck somehow by condensing something with which it doesn't commute. But so that it's not Abelian in the sense that its quantum dimension is bigger than 1. But is there a way to act with a unitary in its degenerate subspace, or is there a way to fuse it with something else?
Yeah, that's a good point. And also, I mean, I didn't even demonstrate to you that we could still isolate them or create them in isolation to sort of say that they have a well-defined existence, but you can actually do that. So I think the important point is that you can sort of show fractal / string operators that move them around, and then you can use these things to define braiding. And to even define quantum dimension, you want to be able to make a whole, some collection of them that has an increasing number to define this. And you can do that too.
Is there a simple physical realization of the unitaries that act on the degenerate subspace?
Yeah, so these are inherited from the 2D layers again, but I could show you a picture, I think, which is related to this fractal spin liquid defect network. So in this defect network, it's very similar to before, except now I have these layers in blue. Okay, I can do this folding trick, pick some gap boundary. It's similar to before, except I have to tie these B and these A anions to the gauge charge and fluxes. Okay, so now what I get is like these kind of hoppings through the one strata. And the important one to look at is this one. So I can move one of these A minus anions, which are going to be my non-Abelian ones, through the one strata up to creating this arc of M excitation, which will be my gauge charge. Okay, so then if I want to do something like make a string, say I want to make a string operator of these A minus anions, because that's like the basic ingredient. You need like the string operator in the layer, but now it's going to have to be attached to something if I want to isolate the string operator from having some excitations near it. So say I move this one over, then I make this sort of line. I could keep moving it, but I haven't drawn enough picture to show that. I'd make this line of like these arcs or gauge charges along the line where I moved it. So I can't use this thing yet to define some good braiding process because the string operator is right next to a bunch of excitations. So the braiding's not going to be well defined. Okay, but I can then move these things away using this sort of fractal evolution rule. And so what you need is that you kind of get a line where in this case you get a whole bunch of ones in a row, which happens here. And this will create some huge sort of cascade of these anions again, but there's some fusion channel where you pair these guys up and get rid of them. So there's going to be some topological operator that acts, that acts sort of, on all of these plaquettes and also on these strings here that can create this kind of excitation pattern. And you can do like a much larger version of this. So you can isolate, to begin with, you can actually isolate the A minus anions arbitrarily far away from each other. You can also, within a single layer, you can enact some string operator that moves a pair really far apart up to doing this fractal operator and another string operator in a different layer. And then I could imagine having this string operator braiding with some other string operator going in the orthogonal direction in that layer that uses a similar shaped excitation. So this is how you define like the braiding between these things. And then if you kind of arrange these nicely, you can have one fractal coming from above and one from below. And then really the only way they talk to each other is via the string operators in the layers. So that's how they end up essentially, just inheriting exactly the braiding unitaries and the degenerate subspaces from the layers themselves. I hope that answered your question.
Yeah, thanks.
I have perhaps a related question.
Mm-hmm.
So let's formulate a more naive question. The fractal can't move. So if it can't move, how can you braid it?
Oh, yeah, that's a good question. So I think this is because when we say they can't move, it's not strictly correct. They can, of course, move, but they can't hop. So in most of these models, or the way I understand it, you have some translation action, and then you can take some sector and you can translate it on the lattice. And so you can call that somehow the translated version of the sector. And then usually, or when I say you can't move, I'm being sloppy. And what I mean is there's no hopping operator that takes this sector and just moves it to the translation version of itself without anything else. You can take it and you can make a whole bunch of other stuff in some other location. And so then the first thing to check is, of course, that can you actually like isolate this single fracton and not have it be part of like a loop excitation or something. But in this case, you can. And then you can try and talk about these like fractal operators in this case that create the isolated excitations, and you can define sort of well-defined braiding processes between them. I think Mike and Sri have a nice paper kind of trying to define these things more carefully.
So let me see if I understand. Within the enriched system, there are excitations which are photonic, but you have something that can be interpreted as moving.
Mm-hmm.
Right? Now, this something is probably not unique. There's several different ways of doing it.
Mm-hmm.
Then is it clear that the braiding you would get from these different ways of doing it would be the same? Because for ordinary anions, we know they can move. We move them, and there's a unique way to do that, and you can prove that what you get is independent of how you do it. Is it clear here? Because you add a lot of extra stuff that is not part of it, which is not intrinsic to the problem.
That's a good point. I think there is trickiness in defining these processes so that there could be like, the way you move a pair around each other could give you different results given if you start them in different locations, of course, and also maybe if you move one around the other versus one, it's not like reciprocal possibly. But I think there are still topologically protected phases that sort of act on some degenerate subspace that can't be lifted. But then exactly how you define them could change the answer, I think is what you were saying. That I agree with that. So the way I'm thinking of defining it, the simplest way is like you have some pair you can separate, and then you could have another pair you could separate, and then you could just talk about the process where you apply some fractal operator that separates one pair and maybe does some other stuff far away. And then you apply the one that separates the other pair and does some stuff far away. And then you undo the first operator and undo the second operator. So you can define it in that way. And I'm not sure if that would match, say, if you just fix some sector somewhere and then somehow move the other one around it. In some cases, you can't actually move the other one around it in a well-defined way, even though the first thing you can do. So yeah, I think it's a bit unclear. Maybe there's a bunch of different processes that don't match you can make between these things.
I also have another kind of very broad question. You're trying to describe these systems using the language of topological field theory, but the systems are not topological. So for example, they depend on the foliation of the manifold on which you put them. It's not clear to me that, and even for a given foliation, the answers depend on some metric, like the number of layers you have in the system. So holding the system size fixed, adding layers is kind of changing the size of the system. So in other words, the system depends, the answers depend on a lot more data than just the topology of the manifold and the topology of the trajectory of the endion. So it's related to the previous question. Since you have more data, it's not clear to me that the language of topological field theory and grading and all that is really the appropriate one.
I think it's sort of, I guess, well, with this topological defect network, which is, I guess, the most coherent version of all this, trying to use topological order to describe these things, it's definitely important, like the combinatorics or whatever, or the extra structure you have of how you put these things together. And then the topological order stuff we know is all just going to give us some ingredient list that we put into the recipe. But then to actually solve the properties of the model you get out from that, it has all this other stuff that in some sense is beyond, well, you could say it's beyond the stuff you put in, although I think you should be able to work it out given how you stitch together the topological order pieces in the first place.
But the problem is that the extra stuff goes beyond topological information. So if I understand correctly, you put the TQFT on every layer, then you couple the layer in sort of a topological way. But the layers themselves break the topology. The way the layers wrap say if you are on the torus, the way they wrap the torus, how many layers there are, all this information is not topological.
Yeah,
so
I think
each layer on its own is topological.
Yeah, I think I'd agree. It's sort of additional. To describe like a full system, you need to have exactly the geometry of the defect network, basically. And in some sense, you could say that part is beyond topological. So once you fix the geometry of the defect network and then you have all the topological ingredients, you can calculate everything. But it's until you fix the geometry of the defect network, you haven't fully specified your model, I guess.
Right. So the simplest way to say that is if you compute the partition function and you scale the system, the answer is not the same, because the number of ground states is going to be different. But everything else, the braiding and all that, might depend on that. So when you braid two endions, I don't see whether the answer depends on how many layers you crossed along the way or not. Does it depend on it or not? Did you braid them kind of only near each other so that you don't cross any other layer, or does it depend on them? If you start braiding them at a far distance, then you cross many layers and the answer could be different.
I think, well, definitely probably in this example, but definitely in other examples, the exact positions of the anyons relative to each other when you start can change the answer of the braiding, right? Because the anyon in this position versus this position, it's a different super selection sector. That's definitely true. But I guess the only thing we're saying is that you should be able to calculate it from some braiding process happening in the topological parts. But this braiding process could depend on exactly where these things start in the defect network. That's kind of, I guess, combinatorial or geometric data.
So to summarize, what you call by braiding these anyons or fractons depends not only on the braiding, but on a lot more information, like where they are, exactly how you braid them, etc.
Yeah, I think I'd agree with that. Yes, it's just the only thing we're saying with the topological defect network construction is that it should be derivable from some topological braiding process. But then, say if you start with two anyons in two different locations, the way they braid, it might come from some different part of the defect network. So it could be a different answer, of course.
I see. Thank you.
So it looks like Nat has a question.
Yes, I was wondering, in Benny's paper, he has this type 2 construction. So I was wondering, like, what goes wrong if you said you couldn't get type 2. So
yeah, that was the whole what I was kind of thinking of and why I thought about this, because I wanted to try and get a type 2 model. But I guess the most basic thing that goes wrong is, so what in the full construction of this, I didn't really say, you have like this fractal in one plane, and then you have this fractal in the other plane. You can pick them to be different. And so I was hoping like, oh yeah, maybe that could give a type 2 model, but it doesn't, okay, because you still end up with all this line-ons and stuff. You could try and couple directly these layers or some other thing to one of Benny's type 2 models that have like a choice of two independent fractals or independent cellular automata rules in the two directions that are best non-trivial. But the basic problem I run into with this and any other idea I've had for trying to kind of couple layers to some fractal gauge fields is that you kind of need that the fractal symmetry acts on the layers in some way that you can realize the symmetry of the layers, right? And so you have, in the layers, you have like these string operators. And if you have this more complicated fractal symmetry, so in this example, right, I made it so that the fractal symmetry would hit the layers in like string operators, which was very convenient because then I could say these string operators are just some string symmetry from a layer. But if you kind of have this more complicated fractal symmetry, it hits the layers in some like garbage way. It looks like a weird fractal symmetry that, and so you don't have a fractal symmetry in your layer, in your individual layer. Sorry, I don't know if that.
You mean you cannot write it as the anyons of the layers explicit as the string operator of the anyon? Or...
Yeah, basically, or in some other wording, I can't find some natural like appropriate fully fractal symmetry, not fractal / linear symmetry of a set of layers in the first place.
Mm-hmm. Okay, thank you.
And yeah, actually, I wanted to raise that as a question. I didn't get to my question slide, but if anyone has any ideas like why, or if you could do some kind of no-go result about non-Abelian fractons in type 2 models, I'd be interested in hearing about that.
Great. So if there aren't more questions, I think at the moment, I think maybe this is a good time to thank Dominic, and then we'll stop the recording. But if people want to stick around a bit for some informal and unrecorded discussion, we can do that at least for a little bit. So thanks again, Dominic, for a very nice talk.